Hello, I'm Omnik. I will participate in the first educational round, and I'll try to explain what I'm doing. In problem A, I given a palindrome, and we need to check if it is possible to rearrange the letters to get a different palindrome. So we can have palindromes of even or odd lengths. In a palindrome of odd lengths, there is a middle symbol that is not paired with anything, but it must be the only symbol that has odd number of occurrences, so we cannot change that. So in both cases, we have pairs of symbols that should be equal, and they have to remain equal after we rearrange them. So the only thing we can actually do is to rearrange the order of those pairs. So if there are two pairs of different symbols, then we can swap them and we will get a different palindrome. Otherwise, we will not. So, as you can see in the sample, we actually need to check if in the first half of the string there are two different characters. I only need to iterate over the first half, so I can just delete the lens by 2 right away. And if I find two characters that are different in the first half, I can just return true and print yes, otherwise I will return false. This is often squared, but the limitations are very small, so it's okay. You can do it in linear time. For example, you can just check if there is a character that is different from the first one. If there is if there is a character that's different from the first one, then you have found a pair of different characters. Otherwise, all of the characters are equal to the first one, so they're equal to each other. Problem B, we have an array where all the elements are different, array of numbers. We have to do exactly k operations, and in one operation we can either remove two minimum elements or remove the maximum element. We want to have the maximum sum in the resulting array. If we sort the numbers, like the sums will not change, maximum and minimums will not change, but now we can the maximums are always on the right side, the minimums are on the left side, so we can either remove two leftmost elements or remove the rightmost element. Now we can see that the order of operations doesn't matter, so the only thing that it is important is how many times we remove the maximum, and all the other operations will be removed into minimums. So if we remove x maximums, then we will remove k minus x minimums 2 times, So it's 2 times k minus x minimums, and the remaining numbers will be just some subsegment of this array. And we can either like calculate prefix sums and just check all the possible options, or like maintain them in some kind of window and move to pointers. But like calculating prefix sums is easier, so why not do that? First sorts the numbers, then calculates prefix sums. So if we remove x maximums, the right border of the segment of the remaining elements will be n minus x. So to get the sum on the segment, we should take prefix sum in the right border minus prefix sum in the left border. The right border is n minus x. The left border is 2 times k minus x, and I should have iterated not to k here. The complexity is n log n due to sorting. In problem C, we defined the characteristic of the array as the sum of absolute differences of the neighboring elements. We are given an array. We need to choose its subsequence, so like drop some of the elements, such that this value, the contrast value, does not change. So the idea here is that basically, like we can like take a number line and put a pointer starting in A1, and then like this pointer should visit all the elements of the array in order, and the distance this pointer traverses is this value. Like this is like the sum of distances traversed between each pair. So since our chosen array must be a subsequence, like we will just drop some of the destination points, but it is easy to see that like we should not change the trajectory. Like, by dropping some points, we can only like decrease the length of this path, and so to achieve that, to achieve not changing the trajectory, we need to keep all the extremes. Like when we suppose we start moving to the right, and then at some point we will move to the left. We have to keep that point like up until which we move to the right. So they're kind of like local maximums and minimums, but we need to be careful here and not like be careful with equal elements. Like we can have this plateau like staying at the same point, and we need to be careful not to remove all of them if this plateau is actually extremum, and not to keep more than one, and to be able to remove all of them if it is needed. I think the easiest way is actually saying like let's look at the direction we are moving, and each time we are changing the direction we have to put another point there. So yeah, we will read the array and look at the direction we are traversing. But if we are staying at the same place, we're just saying that we're not doing anything, we're not changing the direction. Like we still is moving in the same direction in which we were actually moving the last time. And then the answer is like the number of changes of direction plus some constant like to have like start and finish. But again, need to be careful if like there are no changes of direction, maybe start and finish are the same, maybe not. So we were staying at x, now we're moving to y. So we're interested in the sign of y minus x. If this is 0, we don't have to do anything, but I will represent it by empty body because I need to like change x into like in the end I have to say that I'm now staying at y. And if we change the direction, then increase answer by 1 and say that new direction is this one. In the beginning, we say that we don't have any direction basically, so the first time we will actually be moving, we will be changing direction, so we will create a new point. And I think that's just the answer. Well, we do have case when we are not moving actually. and the case when we are moving in the same direction all the time. So I'm pretty confident it should be fine. So in problem D, we have an array of n integers. Apparently they can be red or blue. Initially all the elements are red. Can apply the following operation to the array multiple times. And in the is operation, select one element of the array, and if it was red, then increase it by I and make it blue, and if it was blue, then decrease by I and make red. Then we ask to answer Q queries. If we do exactly K operations, what can be the largest minimum? So we want to maximize minimum. That usually tells us to apply binary search, but maybe no. The operation don't affect the array, so all the queries are asked on the initial array. And there is a hard version of this problem with an NQ up to 200,000 and an easy version with 1,000. So that means that like for every element we are alternating pluses and minuses. And we need to do exactly K operations. Okay, so if we apply some operations to an element, then we increase by x1, then decrease by x2, then increase by x3, then decrease by x4, and so on. So it is like plus sum of xi times minus 1 to the power of I plus 1. We need to do exactly K operations. So we have the sum of all the elements in the array, right? The sum changes also according to these rules, but since we can choose to apply operations to different elements, like the sequence of signs should be split into n alternating sequences. since we know k and we want to maximize something, we probably should the last n operations, assuming that n is at most k, should be pluses if possible. We cannot have more than n pluses in the end because some of these two pluses by pigeonhole principle will be applied to the same element, and that's just impossible. There should be a minus between them. So we must put a minus here, but now we have an element to which we can apply a plus. And so like for every suffix of operations, the balance of pluses and minuses cannot be greater than n if we do it from the end. And moreover, like for every element, it is also true. But we should also start from the plus. So this is possible only if like this prefix is of even length. So in this case we can do something like this, and that just works like all of those pairs give minus ones, and then we have these pluses. If we look at a particular element, we care about maximizing the minimum element, so probably like let's say that in our initial array there was one very small element and all others are big, then we should probably focus on one element, right? So for this one element, like we only looking at the operations that are applied to one element. So they will be alternating, and still we can pair like each plus with the next minus. Maybe there will be one plus in the end, but still like every such pair will have negative impact. So we cannot increase any element by the value bigger than like the position of this last plus. And actually if we will apply more operations in this last plus, it will be strictly smaller because like every such pair will be negative. So if we can do this, like we have these pluses that we should distribute between elements, and then these pairs that give us -1, we can just split between elements as we want. So we can decrease some elements by one, some number of times. Like, I mean, we have to do it, but it is actually not bad for us. Like, this is the maximum increase to the sum we can get, and like, if using these pluses, we can make let's say that we want our minimum to be at least d, and using these pluses we can make all the elements to be at least d, and like the total sum is enough. Like we need minimum to be at least d, so we need sum of the elements to be at least d multiplied by n. this is a necessary condition. It is not sufficient, but if we can, using those pluses, we can make every element to be at least d, and the sum, like including all the changes we did, is at least d times n. Then using those like minus ones, we can just decrease elements that have this opportunity to be decreased but still remain not less than d. So this is good. To be able to check if we can do this, like, can increase it to be at least d, we need to check that using those last n operations we can make them to be not less than d, and the sum is big enough, which is not hard to check. But that if this length was even. If it was odd, then well, something bad happens, because with this greedy logic, like, we will have to start with minus, but we know that we have to start with plus. So like there will be a plus in the beginning. This thing is of length n. But still, like, if we go from suffix, every balance of pluses and minuses should be bounded by n, including this balance. And because of parity, we understand that here balance will be n minus 1. So here it was n minus 2 before this first plus. So if we like just draw the basic greedy thing, then we have to replace at least one plus with a minus. And it actually, like, it cannot be this one, because in that case we will have plus minus minus, but like if we calculate balances from left to right, they must be non-negative. This is kind of not nice. Okay. It's just impossible to change any of these minuses. Oh, right. We can show that if we calculate balances from left to right, in this position the balance must be odd, because the length of this thing is odd. So it is at least 1, because it is non-negative and odd. But that means that it is impossible for all these n operations to be pluses, because after that the balance would be like n plus 1. That's bad. Balances should be at most n. So one of them should be a minus. Well, I guess we don't have anything much better than to just say that this is a minus. But then we can make this one a plus. But then we have to make this one a minus. Plus and so on, minus, like flip all of those. Is it actually true? Well, it looks like it is, yeah. Like for the purposes of like having the biggest sum, this is the best we can do. Let's say that n equal to 1 we will just treat separately. It's very easy, like we don't have any choices, so we just apply the operations we have and just check what will be the value. But here yeah, okay, looks like we cannot do anything better. So like kind of similar to what we had in the good case, we'll have those pairs, like it's actually plus minus. So like up until this point we will have pairs that give us -1, and we can give them to elements as we want, and then we have n-1 pluses in the end, so we can choose n-1 elements and increase them. So, well, that we do greedily, like give the best increase to the smallest element, the second best to the second smallest element, and so on, as we would do here. But the biggest element will not get an increase, and that seems like not good. But from parity reasons, we understand that it is impossible for all the like individual sequences to end in plus, because otherwise we would get this case. And so there must be at least one or like odd number of sequences that will end in minus, and when the sequence ends in minus means that we don't have this last plus, but still every pair of plus and minus after it will decrease the value. So there must be at least one element which will not increase after all our operations. And considering that, that there must be an element that is not increased, we have done the best we could. Okay, so we have our values. Let's sort them. And then, like, to answer the query, we need to look at the parity of k minus n, but since n is fixed, it's just the parity of k, except if k is small. If it is smaller than n, then we will only increase elements, but only k of them. And that need to be handled accurately. Well, okay, let's just start implementing, and we will look at the cases we need to handle. Sort the elements. So then we have three fairly separate cases. When first case is when k is smaller than n, and in that case we will take a prefix of our numbers, like the smallest of them, and increase them in decreasing order, like k to the smallest, k minus 1 to the second smallest, and so on until 1. But then on the suffix, the elements will remain the same. So to calculate the minimum element after we do all of that, we need to be able to separately take prefix, add this decreasing sequence to it, and take minimum, and take minimum on suffix. Minimum on suffix is easy, like it's just suffix of elements as they are now, so we can just for every suffix pre-calculate the minimum. What for prefix? For prefix we need to add k, k minus 1, k minus 2, k minus 3, and you can notice that to each element, to element of the position I, we add k minus I in zero indexation. So we can take elements minus I, and then we, like on prefix, we will take that thing and just add k to all of them. But adding k does not change like the position of the minimum. So instead of taking minimum of values plus k, we can take minimum of values plus k. So we will pre-calculate, and we need to pre-calculate minimum on all the prefixes, but now the array is fixed. It's not the given array, it's ai minus I, where I is the index in sorted order. I'm more or less sure that the answer can be negative, right? Like if n is 1 and k is even, we will have plus 1 minus 2 plus 3 minus 4 and so on, which means that we can like end up with minus k over 2. So yeah, I need to initialize with some kind of, well, it doesn't matter. Minimum for empty set should be like plus infinity. So there we need infinity for sure. But that infinity don't have to be like super big. 2 billions would be enough, but I'm playing safe. So for prefixes, we are calculating minimums on prefix of values ai minus I. On suffixes, we are calculating minimums of just ai. Okay, so using these precalculations, we will be able to answer queries where k is less than n or like at most n. So let's say that in the end we will have to answer queries. And we will have three cases here. So if k is smaller than n, then we are saying that the answer is minimum of, we have to take prefix of size k, and on it take minimum of ai plus k minus I, but we have minimum of ai minus I, and to that we will add k. And on the suffix of size n minus k, just take minimum of ai. That's the answer. Otherwise, we have to we'll have two cases depending on parity of like number of elements here. Number of elements here is n minus k. So if n minus k mod 2 is 0, so k minus n, it's the simple case where we add big numbers to everything and then just decrease some value by 1. How many times? K minus n divided by 2. Okay, we have k minus n signs here, and we need to split them in pairs of plus and minuses. Each such pair will give us -1 that we have to apply. And what we need to check is that minimum of all the elements after applying this thing is at least d, and that their sum is at least d multiplied by n. Not their sum, but the sum of them minus the number of -1s we apply here. So to calculate their minimum, we already have what we need. It's in minpref. Because, well, it's similar to what we did. Like we're increasing the smallest by k, then the next one by k minus 1, by k minus 2, and so on. So the minimum of them will be just minpref of n plus k. What about the sum? Well, the sum we didn't calculate, but we can, right? So we can do it similarly, right? We can calculate the sum of ai minus I, and then just increase it by k times n. So the sum is the sum we calculated previously plus k times n minus the number of minus ones we needed. That's k minus n over 2. So now the answer is the largest number that is at most m, and multiplied by n is at most s. So it looks like a minimum of m and s divided by n rounded down. That would be correct if we would round down correctly. To do that, we need to be super careful because C++ rounds numbers to 0, not down. So negative numbers will be rounded up, actually. Like minus 3 divided by 2 is minus 1, but rounded down it should be minus 2. So if s is negative, then the actual value we need is s minus n plus 1 divided by n, otherwise it is s divided by n. And the answer is minimum of m and s. Okay, that was the simpler case. The harder case, when this is odd, is here, and we have only n minus 1 free pluses. But the idea is still the same. Like we still need the minimum value after we apply those n minus 1 pluses and the sum, and then do the same thing actually. So like the solution should look kind of the same, except min pref we should only take from n minus 1 elements because we are adding something only to them, and also take minimum with the last element just by itself, or I could use min suf of n minus 1. The sum, again, kind of similar, except we added something only to n minus 1 elements. I'm now thinking if this would be correct for n equal to 1. It probably is, but it's better to, well, at least check it. And I think it's better to just hard code it anyways. But yeah, so the sum plus k times n minus 1, that's how much we added. But also in the sum we added elements minus I, but for the last one we did not add anything, we didn't subtract anything yet also. So we need to add this n minus 1 back, and minus the number of pairs, but it is plus 1 here because well, this division would be rounded down, but we actually added one element from those n pluses to make all the pairs, so it should be rounded up. And yeah, that should do it. Let's check the samples. Sure, I can print it with spaces if you so insist. So yeah, it works on samples. What if n is 1? Well, this should work anyway. This probably also should work anyway. Yeah, I will have 0 pluses there, but it's still fine. Yeah, let's just try to submit. That is an insanely hard problem for position D, but also like it is 2 problems, which is like unlike usual code first rounds, it will be just 2 problems in ICPC style. But yeah, well, nice problem, I guess, but it is very hard, I'd say. Alright, problem E. Combinatorics problem. Yay. Is it yay? All right. So we asked to calculate some kind of convolution of given array with binomial coefficients, but the n is very big, so we cannot just use FFT there. And the array is given in some kind of linear generator, pseudo-random, because 10 million numbers is a lot to read. Okay. And k is small. K is up to 5. Well, I know what to do. I was trying to think of ways to somehow explain it, but yeah, let's not do that. So the idea is to calculate dynamic programming. It will be kind of like number of ways to reach a specific cell, moving down or right, and moves down will correspond to like our number k. And so the idea is like the number of such paths from like cell with coordinates I0 to coordinates with to cell with coordinates j. We probably need like k minus 1 here. So the number of such paths will be actually just k. Yeah. The number of such paths is the binomial coefficient, like it's number of paths in the grid with coordinates j minus I and k. So it is j minus I plus k, choose k. And this is actually what we want. Like we want in the cell to have like numbers AI multiplied by these binomial coefficients, with like the smaller indices should be multiplied by bigger binomial coefficient. So we start by saying that we have those dp values, and then just calculate this table, and outputting like some part of this row, like the first values will actually correspond to this. Like the first non-zero value in the array B will be when we have k choose k. If k is 5, then like all of those are zeros. So the first non-zero value will be bk, I guess. So starting from bk, and it will be like here, and it will be just a1 because it's like the only pass here from a1. That's the problem. The solution works in of n times k. Not sure you can easily like come up with this on your own. So yeah, implementing it actually means like how to calculate this GP. Well, we will push like in this row, then we will push all of them down, then we will push in this row, push all of them down, push in the row, and so on. Action of pushing down, we can say like just do nothing. Say that this array now represents the next row, and then we push forward. But pushing forward is just calculating prefix sums. So the solution will be calculate prefix sums k times, and print k minus 1 zeros, and then n minus k plus 1 first elements of the array. Amazing. You probably don't even need like even O of n memory. You can just store the last column. Well, you could have done this with GP too, so doesn't matter really, but each next element is generated as previous element multiplied by x plus y modulo m . So I need to output XOR of values that I get by taking is value multiplied by I without taking modulo. So I will iterate over the index because I need to multiply by it. So this is inclusive actually. And it should look something like this. Except it's not AI, it's AI minus K. First K minus 1 elements are zeros, then element with index K is the first non-zero, but that's A zeros. Well, that's interesting. Some data would be nice. Right. If we need the case row, then the number of rows is k plus 1. Problem F, we have some computer game about zombies. Defending the base. Zombies are waiting for X minutes. There are entrances every minute. One zombie attempts to enter through every entrance. Can defend the entrances either manually or automatically, whatever that means. If an entrance is defended either or both ways during some minutes, no zombie goes through. Every entrance is defended by a single dedicated survivor. Each entrance is defended manually from minute Li until Ri, non-inclusive. Okay. There are key generators. Every entrance should be connected to exactly one generator, but a generator can be connected to multiple entrances. Each generator will work for exactly m consecutive minutes. Okay. So like we need to split the entrances into k groups, and for each group we can choose a segment of length m that is covered. Polycap is a weird gamer. He wants the game to be as difficult as possible, so he wants to connect each entrance to a generator and choose the time in such a way that as many zombies as possible enter the base. Okay, so we want to we have to turn the generator on. And that segment of length m, when we are protected, must be inside the inside the round fully, and m is at most x. And we have the segments when it is protected for sure. So we want to have maximum intersection. Kind of looks like a flow, but DP is more likely. So we need to split our segments into k groups. Some of groups may be empty. Then for each group we have to choose a segment of length m. Then we calculate the intersection of each segment for this, with the segment chosen for its group, and we want to maximize the sum of those intersections. Okay, so we will make two kind of opposite statements, like to understand the structure of the optimal solution. In one statement we will say that let's fix split into k groups. And see what how should we choose the segments for each group. Now it's an independent problem for each group. So for a group, or actually we need to choose a starting point of a segment, right? We have this it's called x in the problem, but that's stupid notation. Let's say t, like the time when the game ends, and we need to choose the starting point such that this segment of length m starting from the time L is inside our gaming time. So from here we can understand that left border of the segment should be from 0 to t minus m. And that's the parameter that fully describes the chosen segment for this group. And so for this L we can look at the cost of doing so, or like profit of doing so. We want to maximize the sum of intersections. Let's look at just one segment. So let's say that we have a segment like here. It can actually go further here, but it is not really important for our purposes. And let's say that m is rather short. Then until we like when we are moving L from 0 to the right, this segment will not intersect our segment at first. Then when the distance from this left border to this left border of our segment is exactly m, the length of the intersection will start go up. And then this segment will be fully inside, and it will remain fully inside until the right border reaches this right border. And then it will go down to 0, and then continue to be 0. Well, actually it will go down like here. So the actual picture should be like this. So this is the same point, this is the same point. This length is m, this length is m. We can have different kinds of segments, like for example, like different m, but with the same m, even like we could have had the segment that intersects with the leftmost position already. like this. Then in 0 we would start with some non-zero value, then reach the maximum here, and then like here it should reach 0 and something like this. So this is our function. Or we can have a segment that ends, like for example at the moment t. Then we will never reach this zone of 0, but we are starting in 0, and then we'll go here, and then it will remain inside up until this point. Or maybe it will start to decline, but don't reach 0. Or actually we can have a very short segment, in which case we will not reach this value of m. Like the maximum intersection can be at most length of this segment. So this will actually look like this. Not like this. So until left point is here, we will have maximum value, and once right point reaches this right point, we will have maximum value. So it's something like this. What's important here is that like this function is piecewise linear, and then when we can draw this function for every segment in our group and then sum them up. Their sum will also be piecewise linear, and the points where we change the derivative of the function, like the line which our graph follows, will be one of those initial changing points, and they are described by saying that either left border or right border of the mixed segment coincides with the left or right border of the one of the segments in the group. Also, it that is the full statement, and what I want to get from it is that to choose the optimal position, we need to be in this break point or on the borders of our of the borders of the viable parameter. Like it can be 0, it can be t minus m, or if it is inside, then we can move both to the left and to the right. And if we are on the straight line in the function, at that point, one of those is non-negative increase. So one of them is not bad, and we can follow it until we reach the breaking point. And thus, since m is fixed, the like we have all of n possible starting positions of our segment, because it should be either 0, t minus m, or like from those sets. Union of those things for all the given segments. So we only have like 8,000 possible starting points. So that's for the like if we fix the split into the k groups, then for each group we can independently choose the best position of the segment to maximize the intersection with this particular group, and we have shown that the possible starting points are like, limited in options. Now we will do the opposite. Let's fix k chosen segments. And now we want to like split the segments into groups, and for each group we already have a segment. So basically for each of the given segments we need to choose one of the k like this generator segments that are already fixed. Then which one to choose? Well, the choices are independent. So for each one we want to choose the one that intersects with us as much as possible. But that since our chosen segments have the same length, I state that we can do the following. For every chosen segment we can draw the midpoint of that segment, and we will just choose the segment with which midpoint is closest to our midpoint. Let's say that we have our segment like this. Its midpoint is here, and this is the closest, and yeah, their intersection is the biggest. Why is that? Well, because like we can write the length of their intersection as a function of the distance between the midpoints, and the closer the midpoint to the other midpoint, the larger will be the intersection. For the segments of fixed length, it is just always true. And so for fixed chosen segments, we just choose the closest by midpoint. What does it mean for us? It means that we can actually do dynamic programming. And if we sort given segments by midpoint, then for the leftmost chosen segment we will choose some prefix of given segments, then a segment, another segment, another segment, and so on. So like the closest midpoint will, when we move midpoint from left to right, the closest midpoint will move from left to right. Well, there are different ways to define this dynamic programming. Maybe the simplest one that comes to mind is, well, we need to choose exactly k segments, so like we need to store their number. And we can, for example, like store the prefix of our segment that is already covered. And then we will iterate over the next segment of segments to cover. And well, for example, we can choose the best segment for it. Somehow, like I have kind of described the way, but it is not super fast. But it is polynomial. So if we just ignore that k is a separate variable, then n transitions, and we can choose the best transition in some reasonable time. Often squared for sure. Probably we can do it in linear time. So what's next? We can probably pre-calculate the transitions. Transition only depends on the segments, on the segment that we are eating. So for every such segment we can pre-calculate the cost. Maybe. But that wouldn't really help. Well, it would help, but not enough to get accepted. N is 2000. We have this n cube that looks pretty much untouchable. We can fix this issue in a different way by using the first observation I said, that for we only have linear number of possible candidates, and since from here we know that when we are moving to the left, the midpoint should also move to the left. We can introduce another dimension. Well, it's basically current left border of the generator segment or something like that. Or current midpoint, it's the same thing, right? And now we can say, okay, we can either skip this point and move to the next one, or we can say, okay, here I will take some segments and I'm increasing k, but then I can add segments that I will cover one by one by moving covered. So now the with good implementation, we should have constant number of transitions, but the number of states is still n cube. However you would like to do it. So what to do? Lambda optimization, probably. So we need to have some fixed k. Instead we want to do a binary search on some lambda value and say that adding another group costs lambda, so we get minus lambda for that to the score. And we say that this function of k, optimal answer of k, optimal answer of lambda is convex, and to prove that we need to prove that optimal answer of k is concave, I want to say, and that, well, it looks true. I think that we can write it as integer linear programming, like say that there are variable for whether we choose this particular point as like a midpoint for a chosen segment. And then for the segments that are chosen, we will define variables for every of the given segments, like whether this segment goes to that group. The sum of those variables is 1, because every segment must go to exactly one group, and variables can be 0 or 1, and they can be 1 only if we have chosen that segment, but that is done by saying that like the particular variable should be at most the variable, like whether we have chosen this segment or not. The number of chosen segments is k. And yeah, this is integer linear programming. Then we can relax it to just linear programming. And that doesn't seem to change the answer, because making non-integer values seems stupid. Like some of them are better. Like for every segment, there will be the best of the chosen segments. And like it should be better to choose more of them if they're non-integer, something like that. And if we have that, then we can prove concavity by saying that if we take two valid solutions, like taking optimal solutions for k1 and k2, then we can take their convex combination, and their like the convex combination of solutions for k1 and k2 will be a valid solution for convex combination with the same coefficient of k1 and k2, and that means that like our graph will lie like higher than the line containing these 2 points on the segment between them. So by definition this function is concave, and thus we can apply lambda optimization, and that kind of reduces the complexity to n square log. I mean, it does. The issue is like whether it's enough. I'm more or less sure that that's the complexity that the setters wanted. But will it be enough with this kind of DP? Because like this has 4n options. I'm not even sure I have enough memory to do that. I mean, I do. But still, it's a lot. Well, I don't want to figure out how to make this DP working good complexity, so I guess I'll have to do with this one in 16 minutes? Well, should be possible if I don't make some stupid mistakes. N is the lens. It's called L. Okay. Okay, so I want to work with midpoints. So I kind of want to multiply all the coordinates by 2. Instead, I will say that midpoint is like the sum of left and right border of the segment. And I will store the given segment as midpoint and initial length. Then when multiplied by 2, the left border is midpoint minus initial length and the right border is midpoint plus initial length. Now I want to write down all the options for midpoints, like interesting midpoints of the segments that we can choose. Probably better to do it here. I can not care about that and then just check that all the segments are valid, whatever that means. Okay, so these are all the options. Now binary search on answer. Binary search on lambda optimization. So it will return the cost and the number of clusters we used. And if the number of clusters is so I will get maximum number of clusters. So if it is at least k, then I should move left border, otherwise move right border, and left border I think. Not sure, to be honest. dp. I will iterate over these points and decide whether I want to choose it or not. And so dp will store, so in the state I have the size of the prefix that I used. Well, actually, I'm saying that I will use this segment right now, so I'm paying to do that by paying lambda, and increase the number of segments I used by 1, and now I can try to actually do that. By saying, okay, try to for the J segment, if I use is segment, so segment with center BI, what I should add here? What should I add? It's the minimum, no, maximum of left borders. Left border is AI first minus AI second, and BI minus A. Right border is the minimum of AI first plus AI second, and BI plus L. If it is non-empty, add R minus L over 2. And try to update. Or I could have not done that, in which case just use the old DP value. That should be it. Just 9. Just print 9. I'm not sure what I should be printing. Assertion failed. That's great. Well, that's just great. Well, yeah. Guess if many of the points. No, it's just minus infinity. How is that possible? Plus here. So, okay, but what should I print? The largest number of zombies that can enter the base. That's like that's all of them. Then we subtract the length of the protected segments. Then we subtract that k times we cover a segment of length L, but then they actually intersect by this thing, so we can add it. I'm not actually sure that it works on samples. It doesn't. um, one. Wait, what? I get bigger answer. Should be the second here. Yeah. What? No, wait. Should be. 8? What are you talking about? That's not possible. This what is going on? it's not outright insane. Isn't it correct? Oh no. Yeah, I understand. It's n n times l here because every entrance will be protected by a generator. Well, at least it works on samples. Can you submit? Time limit. This log. Here we have n times 4n kind of shouldn't be that slow. Probably this maximums and minimums are not great. some of those are probably not needed. Like if we can move to increase the value, it's fine. So like to be a local maximum, need to change the slope, decrease the slope. So when we increase the slope, like here, decrease, and here also increase. Not necessary. So it was like on the border. Like I optimized 2 times and passed. Oh no, I lost snippet with Pragmas. Well, whatever. Maybe it's compiler. A bit sad, but okay. Thanks for watching. Bye.